Let's prove the Cauchy integral theorem for star domains. So the theorem statement is if you have an analytic function, f, on a star domain, D, then any contour integral of f along a closed curve vanishes. So this is an upgrade on our previous result because it's about any closed curve rather than specifically a triangular shaped curve. And part of the one limitation that's there is that we're assuming D is a star domain. All right. So let's just get started. So let f be a function from D to C, analytic. D a star domain with star center Z star. Now our goal is to show that contour integrals of f along closed curves all vanish. Actually, the point of this is to show that f has an antiderivative, and having an antiderivative by the fundamental theorem of calculus implies that contour integrals along closed curve vanish. So we will just show that f has an antiderivative by constructing an antiderivative. Okay, so define capital F from D to C to be the contour integral. So at any point Z in the domain D, capital F of Z will be the contour integral of little f along the line segment from the star center Z star to Z. Now, this is only a well-defined contour integral if the path is actually a path in the domain of the function I'm integrating. And this is a path in the domain because the domain is a star domain and Z star is a star center. So the star domain assumption makes this contour integral make sense. Now our goal is to prove big F prime equals little f on the entire domain D. This might look kind of familiar. So this might remind you of back when we were showing that if all contour integrals along closed loops vanish, then there's an antiderivative. We proved that by constructing an antiderivative under the assumption that contour integrals along closed loops vanish. And we did something similar to this, except here we didn't say take a contour integral along a line segment. We said take a contour integral along any path from Z star to Z. We just said take any path. Here I cannot say, well, back when we were doing that, I could not have said use a line segment because I didn't know that I was looking at a convex set or a star domain. So I just had, all I knew back then was that I had a path connected domain. So I had to say use any path. And also, back then there was a well-definedness problem. We had to be sure that no matter what path you use, you get the same answer. To make sure that this big F is well-defined. Here we don't have that problem. We don't have a well-definedness problem because I'm saying exactly what path you should use to go from Z star to Z. It's this specific one, the line segment. And in fact, if here I said define this to be the contour integral of f along any path from Z star to Z, just pick any path you want, that would not work. I would have a well-definedness problem because I don't know yet that contour integrals are path independent or that they depend only on endpoint. So I would have a well-defined in this problem. In fact, it would be circular. What I'm trying to prove here, pretty much, is that contour integrals depend only on endpoints. So here is a much more straightforward definition of big F of our antiderivative than we had the last time we did this sort of thing. All right, so the goal is to prove big F prime is little f. So that means we want to prove big F prime of z naught is little f of z naught for all z naught in D. Right, so let's fix some z naught in D. So here's a picture of what's going on. Maybe this is D. Here's a star center, Z star. And I have fixed a Z naught. So maybe here's Z naught. And if you want to know about capital F of Z naught, it's the contour integral of little f along this line segment, not along any other path, along this specific line segment. So if you take the contour integral along this line segment, that would be capital F of Z naught. In order to know anything about the derivative of capital F at Z naught, I need to know about the values that capital F takes, not just at Z naught, but in a neighborhood of Z naught. So, I'm going to focus on a disk at Z naught, which is fully inside of D. There is such a disk because D is an open set. D is a star domain, which means it's at least a domain, which means it's open. So star domains are always assumed to be open. So let R be greater than 0, such that this disk, let's just call it U, so it'll be the disk of radius R centered at Z naught, is fully inside of D. Okay, so now we've got this U. And what we will show, we want this, we will show basically this. That the derivative of capital F at Z naught is little f at Z naught when you focus only on the values of capital F in U. That's sufficient to get this because U is an open neighborhood of Z naught. All right, so this probably seems somewhat familiar. We're kind of repeating an old argument, but some subtle things are different. I'm not saying you can use any path from Z star to Z naught. I'm saying use the linear path. Specifically use the linear path. And I'm not in a context where I know that contour integrals are independent of endpoints. I don't know that. I'm actually trying to prove that. But I am in a context where I know f is analytic, and therefore I have the at least triangular path version of the Cauchy integral theorem available. So somehow that's got to come in. All right, so let's focus on understanding how big F behaves in this disk U. So let Z be any point in the disk U, and let's examine what is big F of Z. So here's a point Z in the disk. Well, we can immediately build a useful triangle. And if we look at the contour integral of little f along this triangle, then you will see big F of Z come out. So let me just go ahead and build the triangle. So we've got Z star to Z naught, then fill in the segment Z naught to Z, and then fill in the segment Z to Z star. So let's give this triangle a name. Let me write this over here. let's just call it triangle, and let's make it the triangle spanned by z star, z naught, z. So it's a path that goes z star to z naught to z back to z star along straight line segments. Now, notice that this triangle, so I claim that this triangle is fully inside of D. How do I know that? So the triangle is actually a union of a bunch of line segments. I have the line segment from z star to z naught, the line segment from z star to z, and all of the line segments in between. The line segments from z star to various points on the segment from z naught to z. So if I take all of these sort of in-between segments from z star to various points on this edge, the union of all of those segments is this triangle. All of those segments are inside D because they're segments starting at z star, and z star is a star center for D. And so this is inside D. It's inside D because it's a union of line segments that are all inside D, thanks to the fact that D is a star domain. So that's really the main crucial point where we use the fact that D is a star domain. All right. So the reason to focus on verifying that the triangle is fully inside D is that this is what will be needed for the Cauchy integral theorem from last time, the one about triangular paths, to apply. It needs the entire triangle, including the inside, to be in the domain. Then, what does that theorem tell us? So, by that previous theorem, the Cauchy integral theorem for triangular paths, we know the contour integral of f, little f, along the triangular path z star to z naught to z and back to z star is 0. So that's because the triangle is fully in D and because f is analytic. So this is where we use the fact that f is analytic. Now we've used the two big assumptions. So this is because f is analytic. That's how the theorem from last time worked. It required f to be analytic and the triangle to be fully inside the domain. All right, well, let's break this apart. The contour integral of f along this triangle. The triangular path is a concatenation of 3 line segment paths, 2 of which are actually values of big F. So we have 0 equals this contour integral, which is the sum of these 3 contour integrals. The one from z star to z naught, the one from z naught to z, and the one from z to z star. And these are all contour integrals of f. And that equals 0. Okay, well, this contour integral along a straight line from z star to z naught, that's just what big F of z naught was defined to be. This is not anything, it's just itself. And this one, well, if it were flipped around, if it were from z star to z rather than z to z star, then it would be big F of z. Well, I could flip it around at the cost of a minus sign. So, minus big F of z. All right, so 0 equals this sum of terms. Let me move this term, negative f of z, to the other side. Let me get rid of this stuff. Big F of z is then the sum of these two terms. All right, well, let me write this higher up. Okay, let me include the dummy variable here so I can do something. This is basically an argument we've made before, but we're making it again for fun. And also to pay attention to what small things have changed. So I will write f of zeta as f of z naught plus f of zeta minus f of z naught. Then this will be, so the contour integral from z naught to z of f of z naught d zeta, that's the contour integral of a constant. So I can pull out that constant, and the contour integral of 1 along the line segment from z naught to z is literally z minus z naught. So one way to see that is to notice that z is an antiderivative for 1. So you could just, or zeta is an antiderivative for 1. So you could just evaluate zeta from z naught to z. Okay, and then the leftover term is the integral from z naught to z along a straight line segment of f of zeta minus f of z naught d zeta. All right, so look at what we have as we are investigating the values of big F on the set U. We have big F of z is big F of z naught plus this complex number here times z minus z naught plus this remainder term. And of course, this now looks like the setup for proving that big F is differentiable. If you didn't know why one would add and subtract f of z naught here, it's just to make it so that this term shows up. All right, if we call this function here r of z, so if we just call this r of z, then our task is to prove that r of z goes to 0 fast enough. So r of z over z minus z naught goes to 0 as z goes to z naught. If we do that, then we will have proven that big F is differentiable at z naught, and its derivative is whatever number is here, which happens to be little f of z naught. Then we will be finished. So that was our goal, right? Was this. All right, I can clean the board up pretty nicely with some editing. So here's the picture again, and here's where we were just now. We have found that for z in U at least, U being this, f of z is this, and we just need to show that r of z goes to 0 fast enough. So here r of z is this, this contour integral of f zeta minus f z naught along the line segment z naught to z. We just need to show this, that r of z over z minus z naught goes to 0 as z goes to z naught. If we can show this, then we will know that this function, capital F, is differentiable with derivative this thing, little f of z naught. Okay, so for the sake of proving this, let epsilon be greater than 0, for the sake of proving this limit assertion. This is actually now no different from what we did before when we were making a similar argument. So if you totally know where this is going and you're bored, you can actually just skip the rest of this video, but it's good to do it again. All right, so we're no longer going to use the fact that f is analytic. We already used that fact when we asserted that the contour integral along the triangular path vanishes. Now we're just going to need the fact that f is continuous for the next part. So let epsilon be greater than 0. There's some delta greater than 0 such that, and I'm using the continuity of f, such that for all zeta that are within delta of z naught, I'm using the continuity of f at z naught, and also in the domain. We have, for all these zetas, we have f of zeta is within epsilon of f of z naught. Okay, so I have gotten this delta by using the continuity of little f at z naught. By the way, I know little f is continuous at z naught because, not because it was directly assumed, but because we said f is analytic, which is much stronger. Of course, an analytic function is continuous. So here we've used continuity, and I'm going to claim that this delta is the one that works for, or is one that works for proving this limit assertion. So let z be in the punctured delta disk centered at z naught. And here's what we want then, in order to establish this limit assertion. We want the distance of this from 0 to be less than epsilon. All right, so let's start by just examining r of z. So another way to write this inequality, probably a nicer way to write it, is just to say we want r of z modulus to be less than epsilon times the distance between z and z naught. All right, so let's just work with this thing, r of z. That's modulus of this contour integral f of zeta minus f of z naught d zeta, which is less than or equal to the contour integral of the modulus. So that's kind of the triangle inequality type thing that we've been using a lot. And now I'm in a situation where I have a bound for this thing. I have a bound for this thing that applies at least for zetas that are within delta of z naught, thanks to the properties of the delta that I got. And actually, since z is within delta of z naught, so if z here is chosen not just to be in this disk u, but to be within distance delta of z naught, then certainly any zeta on the line segment between z naught and z is going to be also within delta of z naught. So the integrand here is bounded above by epsilon. And so this is less than or equal to epsilon, a bound for the integrand, times the length of the curve. The length of the curve is the length of the line segment from z to z naught. Well, that's just the modulus of the difference. All right, so I have what I wanted. This is what I wanted, and I have it. So that proves the Cauchy integral theorem for star domains. If you have an analytic function on a star domain, then it has an antiderivative. That's what we directly proved. And also, therefore, all contour integrals along closed curves in the domain vanish. And also, another way of saying that is that contour integrals are path independent.